Welcome back, everyone. We're going to get started with training algorithms. Before you do anything, I just want to make sure that when you guys open your files, so in this section we have folders with all the files in it. So I want you to make sure you download all the files in the same place so you can access it, okay? And you might have to make a new folder for each lecture because the images may cross over. So make a new folder for each lecture and put all the files in that folder, and that way when you open your folder, the file for, like, this is training algorithms, that it actually loads up correctly and you'll get the images like this. So I want to get started with artificial neurons, a brief glimpse into the history of machine learning. We did talk a little bit about this earlier, but it was too early for us to really get into it because we were still doing statistics and deep learning. But now that you've seen some models where we use clustering and we talk about relationships between various data points, now it maybe makes more sense. So trying to understand how the biological brain works in order to design AI, some scientists back in the 40s, they created a perceptron, which we talked about earlier. So neurons are interconnected nerve cells in the brain that are involved in processing and transmitting chemical and electrical signals. So the input is through the dendrites and the output is through the axon. At the time, they described nerve cells as simple logic gates with binary outputs, multiple signals arriving from the dendrites and then integrating into the cell body. And if enough signal strength was inputted, then it would reach a threshold and then the output signal would be generated. In the 50s, Frank Rosenblatt had his concept of a perceptron, and using that they developed some types of algorithms, and we did talk about the perceptron, so I'm not going to even touch on that now. So let's talk more about the formal definition of an artificial neuron. So we can put the idea behind artificial neurons into context of a binary classification task where we refer to two classes as 1 and -1 for simplicity. So you can see this on our chart, -1 and 1. We want to define a decision function. In this case, we're just going to call it Z, and the so-called net input is Wx plus all the Wx's in the series. If the net input of a particular sample is greater than the defined threshold being this theta value here, we predict class 1 and class -1 otherwise. Basically, we're giving it a binary output, right? So if we hit this threshold, neuron fires. We don't hit the threshold, neuron doesn't fire. And this is in the perceptron algorithm. The decision function is a variant of the unit step function. Now, I'm not going to beat this to death because we can go on and on about this, but basically we've talked about this before, so it should be fairly clear. This model is giving us a binary output, and we know that real neural function and also our algorithms are not giving us binary output per se, but this is the simplest model with a single threshold, and you can either fire or don't fire. So the perceptron learning rule is essentially 2 steps. Initialize the weights to 0 or small random numbers, and for each training sample, compute the output value and then update the weights. In any case, it is important to note that the convergence of perceptron is only guaranteed if the two classes are linearly separable and the learning rate is sufficiently small. If the two classes can't be separated by a linear decision boundary, we can set a maximum number of passes over the training data set, which are called epochs, or a threshold for the number of tolerated miscalculations. The perceptron would never stop updating the weights otherwise. So right here, linearly separable works well. This is looking kind of tight, and it won't work over here. Now, before we jump into implementation in the next section, let's summarize what we just talked about in this general concept of the perceptron. In this diagram, we can illustrate how the perceptron receives the inputs of a sample X and combines them with weights W to compute the net input. The net input is then passed on to the threshold function, which generates a binary output of -1 or 1, the predicted class label of the sample. During the learning phase, this output is used to calculate the error of the prediction and also to update the weights listed here. It's kind of a cycle we've got going. So over here, I want to introduce an object-oriented perceptron API. So we're going to take an object-oriented approach to define the perceptron because this is a Python class, and we can initialize a new perceptron classifier right up here via a fit method. The fit method is here, and we're going to make predictions via a separate predict method. So we have a perceptron object, fit, and then we're going to have a separate predict method. As a convention, we append an underscore to attributes that are not being created upon initialization of the object, but by calling the object's other methods, like when we're using self. Use an underscore. So using this perceptron implementation, we can now initialize new perceptron objects with a given learning rate ETA and niter, which is the number of epochs. Via the fit method, we initialize the weights to a vector where m stands for the number of dimensions in the data set, where we can add 1 for the first element in this vector that represents the bias unit. Remember that the first element in this vector, self, W, represents the so-called bias unit that we discussed earlier. Also notice that this vector contains small random numbers drawn from a normal distribution with standard deviation 0.01. And via Argin normal, so we have this here where Argin is a NumPy random number generator that we seeded with a user specified random seed so we can reproduce previous results if desired. Now the reason we don't initialize the weights to 0 is that the learning rate, or ETA, only has an effect on the classification outcome if the weights are initialized to non-zero values. If all the weights are initialized to 0, the learning parameter ETA affects only the scale of the weights vector, not the direction. If you are familiar with trigonometry, consider a vector where the angle and a vector would be exactly 0, and we can see that in some code. In this code right here where we talk about these various vectors. So this line right here is NP-ARCOS is the trigonomic inverse cosine, and NP-lin-alg right here is a function that computes the length of a vector. So after the weights have been initialized, the fit method loops over all individual samples in the training set and updates the weights according to the perceptron learning rule that we discussed in the previous section. The class labels are predicted by the predict method, which is called in the fit method to predict the class label for the weights update, but predict can also be used to predict the class labels of the new data after we have fitted our model. Furthermore, we can also collect the number of miscalc classifications during each epoch in the self.errors right here. So this is where we collect our errors. So we can later analyze how well our perceptron performed during the training. The np function that is used in net inputs simply calculates a vector dot product WTX. So we can train a perceptron model on this iris data set, and we're doing so. Obviously we import from pandas. We can also bring our data in this way through a link. Now we're looking at this data right here. We've got our label. We have our columns that we used to have. So the 4 columns, and then I guess this is the Virginica species. Kind of seen all this before. We can plot the iris data. Now you can see on our plot, this scatter plot shows the distribution of flower samples in the iris data set along with two feature axes, petal length and sepal length. In this two-dimensional subspace, we can see that a linear decision boundary should be sufficient to separate setosa from versicolor flowers. Thus, a linear classifier such as perceptron should be able to classify the flowers in this data set perfectly. Now it's time to train our perceptron algorithm on this iris data set. And we're also going to plot the misclassification error for each epoch to check whether the algorithm converged and then found a decision boundary that separates the two iris classes. So let's check it out. So we're going to execute this code, and you've got our fit line. So we can see in this plot our perceptron converged after the 6th epoch and should now be able to classify the training samples fairly perfectly. And we can do a little convenience function too to visualize the decision boundaries. And so you can see our decision boundary right here. And this is actually the code for decision regions. You can actually use this in other places. I kind of had to find this somewhere, but this works pretty well for determining the differences between two different regions. Just makes it a lot cleaner. So now we define colors and markers and create a color map from the list of colors. Then we determine the minimum and maximum values for the two features and use those feature vectors to create a pair of grid arrays. So you got XX1 and XX2 in our grid arrays right here via the NumPy mesh grid function. So use mesh grid when you want to do this kind of thing. Since we trained our perceptron classifier on two feature dimensions, we need to flatten the grid arrays and create a matrix that has the same number of columns on the iris training subset, so we can use the predict method to predict the class label Z of the corresponding grid points. After reshaping the predicted class label Z into the grid into the same dimensions as XX1 and XX2, we can now draw a contour plot via matplotlibs function, which maps the different decision regions to different colors. So all that explains this chart. And you can see the plot. The perceptron learned a decision boundary that is able to classify all flower samples in the iris training subset perfectly. Yeah, it can do iris, but we haven't tested to see how accurate it is for all three species. But you can see how cleanly this works, and as we go through machine learning, you're going to start seeing how much more powerful machine learning is compared to simple statistics. It can be quite impressive, and I'm certain that this is the future of the world. So this is an update to the perceptron, okay, the adaptive linear neuron, also known as the Adeline algorithm. And what's interesting about this is it illustrates the key concepts of defining and minimizing continuous cost functions. This lays the groundwork for understanding more advanced machine learning algorithms for classification, such as logistic regression, support vector machines, and regression models, which we'll discuss later on. The key difference between the Adeline rule and the perceptron is that the weights are updated based on a linear activation function right here, rather than a unit step function like in the perceptron, like this. In Adeline, the linear activation function is simply the identity function of the net input, so that WTX equals the product of WTX theta equals the product of WTX. While the linear activation function is used for learning the weights, we still use a threshold function to make the final prediction, which is similar to the unit step function, but we have seen earlier. The main difference between perceptron and the Adeline algorithm is in this gateway right here. So this is basically like an analog function now, right? Because like you can fire this up, and when you do so, you can actually fire the neuron, or you can be below this function. You can have a graded step. Here it's either on or off. Here you have different degrees of being on. That's all. And it just makes it more analog. So actually this lecture is getting long. I tried earnestly to finish this lecture in 15 minutes, but there's no way. So we're going to have a part 2 to this lecture. I hate doing it, but there's just no way. This is too much material. So I'll see you guys in part 2 of this lecture. Thank you.